Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the quiet story of visitors from beyond our solar system objects that carry with them the dust and memory of distant worlds. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. On October 19, 2017, astronomer Robert Werrick sits before his computer screen at the University of Hawaii, examining images captured by the Pan-STARRS telescope the night before. The automated system has flagged something unusual, a point of light moving against the background stars, but not in the familiar elliptical dance of asteroids or comets bound to our sun. This object moves with the straight-line trajectory of something passing through, something that belongs to the spaces between stars. The discovery appears first as a series of pixels, barely distinguishable from cosmic noise, like a ghost materializing from the digital static of deep space observation. Over the following hours, as more observations accumulate across observatories worldwide, the truth emerges with mathematical certainty. The object approaches from the direction of the constellation Lyra, traveling at 26 kilometers per second relative to the Sun, far too fast to be gravitationally bound to our solar system. It has already passed its closest approach to our star and now races outward toward the constellation Pegasus, carrying with it the first confirmed evidence that objects from other stellar systems regularly visit our cosmic neighborhood. The velocity alone tells a story written in Newton's equations, a signature of gravitational freedom that speaks of origins in distant suns. Scientists assign it the designation 1Y Oumuamua, marking it as the first officially recognized interstellar object. The Hawaiian name means scout, or messenger from afar arriving first, chosen by the Pan-STARRS team to honor the observatory's location atop Haleakala, where ancient Polynesian navigators once studied the stars to guide their journeys across Earth's vast ocean. Now their descendants in spirit track a different kind of voyager, one that has crossed not water, but the incomprehensibly larger ocean of interstellar space. Yet, even as astronomers celebrate this historic discovery, a puzzle begins to unfold in the reflected light captured by their instruments. Initial observations suggest Oumuamua reflects sunlight in a pattern consistent with an asteroid, rocky and metallic, rather than icy like a comet. Its spectrum shows the reddish tint of oxidized metals, similar to objects found in the outer asteroid belt between Mars and Jupiter. But asteroids, formed in the warm inner regions of planetary systems where rocky planets coalesce, should not survive the million-year journeys between stars. The cosmic radiation and occasional stellar encounters should have ground them to dust long ago, leaving only the hardier icy bodies to traverse the galactic void. The object tumbles through space in a complex rotation, completing one full turn every 3 hours. Its brightness varying by a factor of 10 as different surfaces catch and reflect sunlight. This dramatic variation suggests an extremely elongated shape, perhaps 10 times longer than it is wide, like a cosmic cigar or needle threading through the solar system. No known asteroid or comet exhibits such extreme proportions, adding another layer to the mystery of this interstellar messenger. The rotation itself tells a story of ancient violence, likely the result of a collision that sent Oumuamua spinning into the void eons ago. Its tumbling motion, a fossil record of that primordial impact. As telescopes around the world turn to track this visitor, astronomers piece together its recent trajectory through the solar system. Oumuamua approached from the north, diving down through the plane where the planets orbit, swinging around the Sun at a distance closer than Mercury's orbit, then climbing back up and outward toward interstellar space. Its path traces a hyperbolic arc, the mathematical signature of an unbound orbit, a trajectory that speaks of speeds too great for our Sun's gravity to capture and hold. The timing of the discovery carries its own quiet irony. Oumuamua has been visible to Earth-based telescopes for only a few weeks when Werik spots it, and it was already past its closest approach to the Sun. Had it arrived a few decades earlier, before the advent of automated sky surveys and sensitive CCD cameras, it would have passed through our solar system completely unnoticed. One more messenger from the galaxy that delivered its secrets to empty space. Had it been discovered a year earlier, when it was still approaching the Sun, astronomers would have had months rather than weeks to study it in detail. The object's small size compounds the challenge of observation. Estimates based on its brightness suggest Oumuamua measures perhaps 400 meters at its longest dimension, smaller than most city blocks. A cosmic pebble barely visible even to the most powerful telescopes. At the distance of the outer planets, it appears fainter than the dimmest stars visible to the naked eye under perfect dark skies. Yet this tiny visitor carries within its physical structure and chemical composition the story of another stellar system, another family of planets orbiting a distant sun. As Oumuamua speeds away from the Sun at 44 kilometers per second, astronomers realize they have perhaps weeks before it fades beyond the reach of even the most powerful telescopes. The race begins to extract every possible piece of information from this fleeting visitor, this first tangible evidence of the vast population of objects that drift in the darkness between stars. Radio telescopes scan it for any artificial signals, though none are detected. Spectroscopes analyze its reflected light for clues to its composition. Photometers track its rotation and brightness variations to deduce its shape and surface properties. The mystery deepens with each observation. Oumuamua shows no signs of the gas and dust coma that typically surrounds comets as they warm near the Sun, yet its apparently rocky nature seems inconsistent with survival during interstellar travel. Its extreme elongation has no precedent among solar system objects, suggesting either unusual formation conditions or perhaps partial fragmentation during its long journey through space. The scientific community begins to grapple with the realization that their first close look at an interstellar visitor has raised more questions than it has answered. Only took 4.5 billion years for one to finally announce itself to human science. Only lasted a few months in our telescopes before vanishing forever into the cosmic deep. Only left behind more questions than answers about the nature of interstellar space and the objects that call it home. Word count: Chanchiwin 1593. The shape of Oumuamua emerges slowly from the mathematics of light, assembled from photons that have traveled across interstellar space to strike silicon detectors in Earth-based telescopes. As the object tumbles through its 7.3-hour rotation cycle, its brightness oscillates with mechanical precision, dimming and brightening as different faces present themselves to the Sun. The amplitude of this variation, a tenfold change in reflected light, tells astronomers they are witnessing something unprecedented in the solar system's catalogue of known objects. Traditional asteroids and comets exhibit brightness variations of perhaps 2 or 3 times as they rotate, their roughly spherical or moderately elongated shapes casting familiar patterns of shadow and illumination. But Oumuamua's dramatic light curve suggests an object stretched to extraordinary proportions, like a cosmic splinter or shard tumbling end over end through the void. Computer models, fed with the observational data, converge on a shape ratio of roughly 10 times longer than it is wide, resembling a metallic cigar or perhaps a flattened disc viewed edge-on. The precise geometry remains tantalizingly uncertain, hidden behind the ambiguities of distant observation. Light curve analysis can distinguish between a long, thin cylinder and a flat pancake-shaped object viewed from certain angles, both of which would produce similar brightness variations as they rotate. The lack of detailed imaging. Oumuamua appears as nothing more than a point source. Even in the largest telescopes forces astronomers to rely on these indirect measurements, like archaeologists reconstructing an ancient artifact from shadows cast on a cave wall. Dr. Marco Micheli at the European Space Agency's Space Situational Awareness Program leads one of the teams analyzing Oumuamua's rotation and shape. His colleagues spread across multiple continents coordinate observations, each telescope capturing a few precious hours of data before Earth's rotation carries Oumuamua out of view. The international collaboration unfolds with quiet urgency. Scientists sharing data and preliminary results through encrypted channels, knowing that every passing day carries their target farther from the Sun and deeper into observational obscurity. The object's surface properties add another layer to the puzzle. Spectroscopic analysis reveals a reddish coloration similar to objects in the outer solar system, Kuiper belt bodies and trojans that have been darkened and reddened by eons of cosmic ray bombardment. This organic-rich patina suggests Oumuamua has indeed spent vast periods exposed to the radiation environment of interstellar space, its surface slowly cooking under the influence of galactic cosmic rays and ultraviolet starlight from distant suns. Yet the surface shows no signs of the volatile ice's water, carbon dioxide, methane that astronomers expect to find on objects originating in the cold outer regions of planetary systems. As Oumuamua approached within 0.25 astronomical units of the Sun, closer than Mercury's orbit, it should have heated to temperatures sufficient to sublimate any surface ices into visible gas clouds. Comets routinely develop spectacular comas and tails under such conditions, their icy nuclei boiling away to create the ethereal displays visible from Earth. Oumuamua remains stubbornly inert, showing no signs of outgassing despite temperatures that should have activated any volatile materials on its surface. The rotation period itself carries information about Oumuamua's structural integrity, an object tumbling at 7. 3 hours approaches the limit of what a loose rubble pile held together by weak gravity can sustain. Faster rotation would overcome the gravitational binding and scatter the constituent pieces into space. This suggests Oumuamua possesses sufficient structural strength to maintain its integrity under rotational stress, either a single coherent piece of rock and metal, or a rubble pile bound by forces stronger than simple gravitational attraction. Computer simulations attempt to trace the object's origin story, written in its current rotation state. The tumbling motion likely results from a violent encounter in its distant past, perhaps the collision that ejected it from its parent system, or a subsequent impact during its journey through interstellar space. The specific orientation of the rotation axis, tilted with respect to its orbital motion, preserves a fossil record of that ancient trauma, like a wine bottle spinning through space, still carrying the motion imparted by some primordial catastrophe. As observations accumulate, astronomers begin to appreciate the statistical miracle of Oumuamua's discovery. Objects of its size, traveling at interstellar velocities, spend only a few months within the detection range of current sky surveys. The vast majority pass through the solar system unnoticed, too small and fast-moving to trigger automated detection algorithms designed primarily to track potentially hazardous near-Earth asteroids. Estimates suggest that several interstellar visitors of Oumuamua's size pass through the inner solar system each year, invisible messengers carrying stories from distant worlds that remain forever untold. The elongated shape itself challenges theories of planetary system formation and evolution. No mechanism in current models produces such extremely stretched objects during the normal process of planet formation. The shape suggests either exotic formation conditions in Oumuamua's original system or significant modification during its interstellar journey, perhaps partial fragmentation that stripped away portions of a larger parent body, leaving behind this elongated remnant. Radio telescopes at the Green Bank Observatory in West Virginia and Parkes Observatory in Australia scan Oumuamua across multiple frequencies, searching for any artificial signals that might suggest technological origin. The search for extraterrestrial intelligence receives its first opportunity to examine an object confirmed to originate from another star system. The radio silence that emerges from these observations eliminates exotic explanations while deepening the natural mystery of this interstellar wanderer. Only took a few dozen photons reflected from its surface to reveal its strange geometry. Only needed a few weeks of careful measurement to establish its unprecedented elongation. Only left astronomers to wonder whether such shapes represent common products of interstellar travel or hints of formation processes unknown in our own solar system. The tumbling rhythm of Oumuamua creates a temporal signature as precise as a cosmic metronome, its 7.3-hour rotation cycle marking time across the emptiness of space. Each complete turn brings different faces of the object into sunlight, creating the predictable rise and fall of brightness that allows astronomers to track its orientation despite the vast distances involved. The rotation itself becomes a kind of clock, measuring the passage of time not in Earth hours, but in the slow pirouettes of an interstellar visitor spinning through the void. Observatory after observatory captures this rhythmic dance of light and shadow. The Lowell Observatory in Arizona records the object's brightness variations through multiple filters, each wavelength of light revealing subtle differences in surface composition across Oumuamua's elongated form. The European Southern Observatory's Very Large Telescope in Chile adds its observations to the growing data set, its adaptive optics systems compensating for atmospheric turbulence to extract the faintest possible signals from this distant target. Telescopes in Hawaii, Spain, and California contribute their own measurements, creating a global network of observation that follows Oumuamua across Earth's rotating sky. The rotation period of 7. 3 hours places Oumuamua near the theoretical limit for a gravitationally bound rubble pile. Objects spinning faster than this critical threshold would overcome their own weak gravitational attraction and disperse into space, their constituent rocks and dust scattered along their orbital path. This suggests that Oumuamua possesses either sufficient internal structural strength to resist rotational disruption, or perhaps represents a single coherent piece of material rather than a collection of smaller fragments held together by gravity alone. Tupet, Olivier Hainaut at the European Southern Observatory coordinates much of the photometric analysis, his team developing sophisticated models to extract maximum information from the limited observational data. The light curves they construct reveal not just the rotation period, but hints about the object's three-dimensional shape and the distribution of material across its surface. Dark and light regions create subtle asymmetries in the brightness variations, suggesting a heterogeneous composition that varies from one end of the elongated object to the other. The tumbling motion itself carries information about Oumuamua's violent past. Unlike the planets and moons of our solar system, which generally rotate in stable, predictable patterns aligned with their orbital motion, Oumuamua tumbles chaotically around multiple axes. This complex rotation suggests it was set spinning by some ancient collision or gravitational encounter, its current motion a fossil record of primordial violence frozen into its mechanical behavior. The specific orientation of the rotation axis, tilted at a steep angle relative to its orbital plane, preserves evidence of the forces that first sent it tumbling into interstellar space. Computer simulations attempt to model the physical processes that could produce such rapid, complex rotation in an interstellar object. Planetary ejection scenarios. Gravitational encounters with massive planets that fling objects out of their parent systems typically impart significant angular momentum to the ejected bodies. Close encounters with stars during the interstellar journey could further modify the rotation state, though such encounters remain statistically rare during the million-year timescales of interstellar travel. The current rotation of Oumuamua thus represents a kind of mechanical memory, preserving information about its dynamical history written in the language of angular momentum and rotational energy. The brightness variations also reveal subtle color changes as different faces of the object rotate into view. Spectroscopic analysis shows that Oumuamua's surface exhibits slight compositional variations, with some regions appearing slightly redder than others. This heterogeneity suggests either an originally diverse composition or the effects of space weathering processes that have modified different parts of the surface to varying degrees. Cosmic ray bombardment, solar wind particle impacts, and micrometeorite erosion all contribute to the gradual alteration of surfaces exposed to the interstellar medium. Attempts to detect any wobble or precession in the rotation prove unsuccessful, suggesting that Oumuamua rotates as a relatively rigid body rather than a loose collection of fragments. This mechanical stability supports models of the object as either a single piece of solid rock and metal or a rubble pile bound together by forces beyond simple gravitational attraction, perhaps cohesive forces between constituent particles, or structural strength inherited from a larger parent body that was subsequently fragmented. The precision of the 7-3-hour period allows astronomers to predict exactly when Oumuamua will reach maximum and minimum brightness, enabling coordinated observations across multiple wavelengths and observation sites. This temporal predictability becomes crucial as the object fades with increasing distance from the Sun, allowing observers to concentrate their limited telescope time during the brief windows when the object presents its maximum surface area to both solar illumination and Earth-based detection. Temperature models based on the rotation rate suggest that Oumuamua's surface experiences dramatic thermal cycling as it tumbles through space. The elongated shape means that different parts of the object receive vastly different amounts of solar heating depending on their orientation relative to the Sun. During each 7-3-hour rotation cycle, surface temperatures likely vary by hundreds of degrees, creating thermal stresses that could contribute to gradual fragmentation or surface modification over long timescales. Radio observations fail to detect any modulation of signals that might correspond to the rotation period, eliminating exotic scenarios involving artificial or technological origins. The object spins silently through space. Its only communication with Earth, the ancient language of reflected sunlight, carrying information about surface composition and geometric structure. Yet, even this passive radiation tells stories about processes occurring in distant stellar systems, migration patterns of objects through interstellar space, and the physical properties of matter that has survived million-year journeys between the stars. Only took 7 hours and 18 minutes for each complete revolution to reveal its secrets. Only needed the mathematics of light and shadow to decode its three-dimensional form from two-dimensional observations. Only left behind the mystery of how such precisely timed tumbling could preserve itself across the vast emptiness of interstellar space. The story of Oumuamua begins in darkness, in the cold outer reaches of a planetary system orbiting a star whose light has never reached human eyes. perhaps 10 million years ago, perhaps 100 million. This object condensed from the primordial disk of gas and dust that surrounded its parent star during the chaotic epoch of planet formation in that distant system. Oumuamua may have been one of countless planetesimals, the building blocks of worlds slowly accreting material through gentle collisions in the gravitational nursery where planets are born. The young planetary system experiences the violent reshuffling common to stellar nurseries across the galaxy. Massive planets migrate inward and outward under gravitational influences, their orbital dance destabilizing smaller bodies throughout the system. Jupiter-sized worlds scatter asteroids and comets like cosmic billiard balls, sending some crashing into forming terrestrial planets while ejecting others entirely from the gravitational embrace of their birth star. Oumuamua finds itself among the exiles, flung outward by a close gravitational encounter that accelerates it beyond the escape velocity of its original home. The ejection event itself unfolds over a matter of days or weeks, but its consequences span geological time. As Oumuamua crosses the boundary into interstellar space, it carries with it chemical fingerprints of its origin system, isotopic ratios of carbon, nitrogen, and oxygen that formed under the specific conditions of its parent star's nebular disk. These elemental signatures become frozen into its structure, preserving information about stellar nucleosynthesis processes and planetary formation conditions in a stellar environment that may differ substantially from our own solar system's history. Dr. Alan Fitzsimmons at Queen's University Belfast leads theoretical studies of Oumuamua's probable origin story, his team running computer simulations that model the ejection of small bodies from planetary systems throughout the galaxy. Their calculations suggest that every star system produces vast numbers of interstellar wanderers during its early formation phase, when massive planets settle into stable orbits and gravitationally scatter the remaining debris of planet formation. The Milky Way galaxy thus contains a vast population of nomadic objects, orphaned planetesimals drifting between stars, carrying within their physical structure the chemical heritage of their diverse birthplaces. The interstellar journey begins with Oumuamua moving at perhaps 5 to 10 kilometers per second relative to its parent star, fast enough to escape but slow compared to the velocities it will eventually achieve. As it travels outward through the gravitational influence of its birth system, the object experiences a final acceleration boost, gaining additional speed that will determine its ultimate trajectory through the galaxy. This gravitational slingshot effect, similar to the techniques used by spacecraft navigating the outer solar system, provides Oumuamua with the velocity needed for true interstellar travel. Once free of its parent star's gravitational well, Oumuamua enters the vast emptiness between stellar systems, where matter exists at densities billions of times lower than the best laboratory vacuum achievable on Earth. The interstellar medium consists primarily of hydrogen atoms and dust grains, with occasional molecular clouds providing slightly denser regions of gas and microscopic particles. Through this tenuous environment, Oumuamua travels in nearly straight-line motion, its path curved only by the weak gravitational influences of distant stars encountered during its million-year odyssey. The surface of the object undergoes gradual modification during its interstellar voyage. Cosmic rays, high-energy particles, accelerated by supernova explosions, and other violent processes bombard Oumuamua continuously, slowly altering its chemical composition through nuclear reactions that create new isotopes and break down complex molecules. Solar wind particles from distant stars contribute additional radiation damage, while ultraviolet light from hot blue stars along its path gradually darkens and reddens organic materials on the surface. These space-weathering processes operate so slowly that their effects accumulate only over millions of years, creating the mature, reddened surface that astronomers observe today. Gravitational encounters with other stars provide occasional perturbations to Oumuamua's trajectory. Though such close approaches remain rare during typical interstellar journeys, when they do occur, these stellar encounters can significantly alter both the object's velocity and rotation state, potentially explaining the complex tumbling motion observed during its passage through our solar system. Computer models suggest that Oumuamua has likely experienced one or two moderately close approaches to other stars during its interstellar wandering, each encounter leaving its signature in the object's current mechanical state. The temperature during interstellar travel hovers near absolute zero, perhaps 10 to 20 degrees above the cosmic background radiation temperature that permeates all of space. At these extreme cold conditions, any volatile materials that survive the ejection from Oumuamua's parent system would freeze into solid form, creating a kind of primordial time capsule, preserving information about the chemical composition of its birth environment. Yet, the object shows no signs of such volatiles today, suggesting either that they were lost during the ejection event or subsequently removed by space weathering processes during the long interstellar journey. Navigation through the galaxy follows the gravitational architecture established by the Milky Way's spiral arms and central bulge. Oumuamua's trajectory carries it through regions of varying stellar density, from the sparse environments between spiral arms to the more crowded stellar neighborhoods closer to the galactic plane. Its current velocity of 26 kilometers per second relative to the Sun reflects not only its ejection speed, but also the accumulated gravitational influences of every massive object it has encountered during its cosmic wandering. The statistical analysis of Oumuamua's motion through local stellar neighborhoods suggests it has traveled roughly 50 to 100 light-years since its ejection, visiting the gravitational spheres of influence of perhaps a dozen different star systems during its journey. Each passage through another stellar system provided opportunities for additional gravitational modification of its trajectory, gradually randomizing its motion until its current path bears little resemblance to its original ejection vector from its parent star. Only took 10 million years of patient travel through the cosmic void to reach our solar system. Only needed a few gravitational encounters to erase most traces of its original orbital motion. Only preserved in its chemical composition and physical structure the faint signatures of processes that occurred in a planetary system now lost to astronomical observation. The acceleration begins as a whisper in the data, a subtle deviation from the perfect gravitational predictions that should govern Oumuamua's motion through the solar system. Dr. Marco Micheli at the European Space Agency first notices the discrepancy in June 2018, 8 months after the object's discovery. When precise astrometric measurements reveal that Oumuamua is not exactly where Newton's laws suggest it should be, the deviation measures only 40 micro-arc-seconds per day, an angular displacement so small it would take 70 years to equal the apparent width of a human hair held at arm's length. Yet this tiny acceleration carries profound implications for understanding the nature of interstellar visitors. Comets routinely exhibit non-gravitational accelerations as they approach the Sun, their surfaces heating and releasing jets of gas that act like miniature rocket engines, nudging the parent body in directions determined by the orientation and timing of the outgassing. But Oumuamua shows no visible signs of such activity, no coma of gas and dust, no tail streaming away from the Sun, no spectroscopic evidence of water vapor or other volatile materials sublimating from its surface. The acceleration vector points away from the Sun with mathematical precision, suggesting a radial force that strengthens as Oumuamua approaches perihelion and weakens as it recedes. This pattern matches the thermal forcing expected from sublimating volatiles, yet all attempts to detect the expected gas production fail to find any evidence of outgassing. Observations with the Spitzer Space Telescope, sensitive to the infrared heat signatures that should accompany sublimating ices, reveal no thermal emission beyond what would be expected from an inert, rocky object absorbing and re-radiating solar energy. Dr. Alan Fitzsimmons coordinates ground-based spectroscopic observations from multiple observatories, searching for the emission lines of water vapor, carbon monoxide, or carbon dioxide that should accompany any significant outgassing. His team employs the most sensitive detection techniques available, pushing the limits of current instrumentation to search for even trace amounts of gas production. The non-detections they obtain place stringent upper limits on any possible volatile release limits, so low that conventional comet-like outgassing cannot explain the observed acceleration. The magnitude of the acceleration itself provides clues to the underlying physical process, at its peak, near perihelion. Oumuamua experiences a non-gravitational force roughly 10,000 times weaker than Earth's surface gravity, barely sufficient to lift a grain of sand, yet persistent enough to accumulate into measurable trajectory changes over the months of observation. This gentle but sustained pushing suggests a process operating across the entire illuminated surface rather than localized jets of the type observed on active comets. Computer models attempt to reconcile the observed acceleration with various physical mechanisms that might operate on an interstellar object encountering solar heating for the first time in millions of years. Thermal recoil affects the momentum carried away by infrared photons re-radiated from the heated surface prove too weak by several orders of magnitude to explain the observations. Solar radiation pressure, which can influence the motion of lightweight objects in space, similarly falls short of accounting for the measured acceleration unless Oumuamua possesses an impossibly low density. The acceleration reaches its maximum strength when Oumuamua lies approximately 0.4 astronomical units from the Sun, well within the orbit of Mercury, where surface temperatures should exceed 300 degrees Celsius on the sunlit side. At these temperatures, water ice should sublimate vigorously, producing easily detectable gas clouds around any comet-like nucleus. The absence of such activity, combined with the clear evidence of non-gravitational acceleration, creates a fundamental paradox that challenges conventional understanding of small solar system bodies. Theoretical studies explore increasingly exotic explanations for the anomalous motion. Perhaps Oumuamua represents a fragment of a larger body that was disrupted during its interstellar journey, with internal structure or composition unlike anything found in our solar system. Perhaps it contains volatile materials that sublime at temperatures lower than typical cometary ices, producing gases too tenuous for current detection methods, but sufficient to generate the observed acceleration. Perhaps the object's extreme elongation creates unusual thermal or electromagnetic effects that concentrate outgassing along specific geometric axes. The rotation of Oumuamua complicates efforts to model the acceleration mechanism. The object's 3-hour tumbling motion should cause any directional outgassing to average out over multiple rotation cycles, producing little net acceleration unless the gas release is strongly concentrated along specific parts of the surface or aligned with particular geometric axes. Detailed thermal models suggest that the most effective configuration would involve outgassing from the object's ends rather than its sides, where the extreme elongation would create the largest temperature gradients and most efficient volatile release. Radio observations with the Green Bank telescope and other facilities continue to monitor Oumuamua for any emissions that might reveal the composition of outgassing materials. The search extends across multiple frequency bands, looking for the characteristic signatures of common volatile molecules as well as more exotic possibilities. The radio silence that emerges from these observations eliminates many conventional explanations while deepening the mystery of this interstellar visitor's anomalous behavior. Attempts to fit the acceleration data with theoretical models of comet-like activity require gas production rates so low that they approach the threshold of physical detectability. Yet even these minimal outgassing scenarios struggle to match the precise timing and magnitude of the observed acceleration without invoking unusual compositions or geometric configurations unlike any known solar system object. The mathematical models converge on solutions that seem to require Oumuamua to possess properties that are simultaneously conventional enough to explain its basic orbital motion, yet exotic enough to account for its paradoxical acceleration. As Oumuamua continues its outward journey beyond the orbit of Jupiter, the acceleration gradually weakens and eventually becomes undetectable as decreasing solar heating reduces whatever process drives the anomalous motion. The final astrometric observations, obtained in late 2018 when the object has faded to the limits of even the largest telescopes, confirm that the acceleration follows the expected pattern of a thermally driven process, strengthening near perihelion and fading with increasing solar distance. Only took the most precise astrometric measurements in astronomical history to detect the subtle deviation from gravitational motion. Only needed 8 months of careful position tracking to confirm that Oumuamua was gently pushing itself through space by some invisible mechanism. Only left behind the puzzling question of how an apparently inert rocky object could accelerate like a comet without showing any signs of the gas production that should power such motion. The absence haunts the observations like a missing note in a cosmic symphony. Every telescope turned toward Oumuamua searches for the familiar signatures of cometary activity, the glowing coma of gas and dust that should surround any icy body releasing volatiles near the sun. Spectroscopes scan for the emission lines of water vapor, carbon monoxide, and methane that mark active sublimation from heated surfaces. Infrared detectors probe for the thermal signatures that accompany gas production. Camera after camera captures images of empty space around the object, finding only the stark point of light that marks Oumuamua's position against the background stars. Dr. David Jewett at UCLA coordinates some of the most sensitive searches for cometary activity, employing techniques refined through decades of studying the solar system's most distant and faintest comets. His team uses the Hubble Space Telescope to photograph Oumuamua at multiple wavelengths, stacking dozens of images to reach the theoretical limits of detection for any possible coma or tail. The composite images reveal nothing beyond the expected scattered light from the object itself, no extended halo of gas, no streamer of dust particles carried away by solar radiation pressure, no asymmetric brightness distribution that might indicate directional outgassing. The non-detection becomes more puzzling when compared to the behavior of known comets at similar distances from the Sun. Objects like Comet 67P Churyumov-Gerasimenko, studied in detail by the European Space Agency's Rosetta mission, begin showing detectable gas production at distances of 3 to 4 astronomical units from the Sun, well beyond Oumuamua's closest approach. By the time such comets reach the orbit of Mars, they typically display obvious comas visible even to modest ground-based telescopes. Oumuamua passes nearly twice as close to the Sun as Mars, yet remains stubbornly inactive to all observational tests. Theoretical calculations of the expected outgassing rate, based on Oumuamua's size and the solar heating it experiences, suggest that even a modest fraction of ice on its surface should produce detectable gas clouds. Computer models of cometary nuclei indicate that objects need only a few % ice content to show obvious activity when heated to the temperatures Oumuamua encounters during its solar passage. The absence of any detectable coma implies either an ice content below 0.1%, extraordinarily low even for asteroid-like bodies, or some mechanism that prevents normal sublimation despite the presence of volatile materials. The search extends beyond visible light into other portions of the electromagnetic spectrum where outgassing signatures might appear. Radio telescopes monitor Oumuamua for the microwave emissions characteristic of water vapor and other simple molecules. Infrared observations probe for the thermal signatures of sublimating ices and the microscopic dust particles they carry along during release. X-ray and ultraviolet observations search for the fluorescence signatures produced when solar radiation ionizes gas molecules in a tenuous coma. Each observation technique yields the same result: no detectable evidence of gas or dust production. Dr. Alan Fitzsimmons leads efforts to place quantitative limits on any possible outgassing from Oumuamua, pushing observational techniques to their sensitivity limits to constrain the rate of volatile release. His calculations suggest that gas production would need to be at least 100 times lower than typical comets to remain undetected by current instruments. Such minimal outgassing rates approach the theoretical threshold where individual molecules sublimating from the surface might not form a coherent coma, instead dispersing immediately into the vacuum of space without creating detectable concentrations around the parent body. The acceleration data provides an independent constraint on outgassing rates, since the magnitude of the non-gravitational force must match the momentum carried away by any escaping gases. Detailed analysis of Oumuamua's trajectory suggests gas production rates of perhaps a few kilograms per second at perihelion, substantial enough to affect the object's motion, but apparently too small to create detectable atmospheric signatures around the nucleus. This creates a narrow window of physical conditions where outgassing can influence orbital motion without producing observable comas. Attempts to model the outgassing geometry focus on configurations that might concentrate gas release into highly directional jets rather than the diffuse, spherically symmetric patterns typical of most comets. Perhaps Oumuamua's extreme elongation creates preferential outgassing from its ends, where thermal gradients are steepest and volatile materials might be most concentrated. Perhaps the object's complex rotation causes gas release to occur in brief, intense bursts aligned with specific orientations relative to the Sun, creating jets too narrow and sporadic for current detection methods. The composition of any hypothetical outgassing materials remains completely unknown, opening possibilities for exotic volatile species that might sublime at lower temperatures or produce gases invisible to conventional detection techniques. Molecular hydrogen, for instance, lacks the strong emission lines that make water vapor and carbon dioxide easily detectable in astronomical observations. Carbon-based molecules might photodissociate so rapidly in the solar environment that they never accumulate into detectable concentrations, despite continuous production from the surface. Temperature mapping of Oumuamua's surface, based on its rotation period and thermal properties inferred from observations, suggests that different parts of the elongated object experience dramatically different heating rates as it tumbles through space. The ends of the object, receiving direct solar illumination for only part of each rotation cycle, might reach temperatures sufficient for sublimation only during brief windows of optimal orientation. This temporal concentration of heating could produce episodic outgassing that averages to very low rates over complete rotation cycles. Comparison with the handful of other asteroids known to exhibit weak cometary activity, objects like 3200 Phaethon and 6478 Gort, reveals that Oumuamua's behavior represents an extreme case even among these unusual hybrid objects. These transitional bodies typically show at least some detectable dust production, even if gas emission remains below detection thresholds. Oumuamua appears completely inert to all observational tests except the subtle astrometric signature of its non-gravitational acceleration. The paradox deepens when considering the object's apparent surface composition, which spectroscopic analysis suggests resembles the organic-rich materials found on dark asteroids and outer solar system bodies. Such surfaces typically contain volatile-rich compounds that should readily sublime when heated to the temperatures Oumuamua experiences during its close solar passage. The mismatch between expected surface chemistry and observed behavior suggests either unusual thermal properties that inhibit normal sublimation or compositional differences not detectable through current spectroscopic techniques. Only took the most sensitive astronomical instruments available to confirm the absence of any detectable outgassing. Only needed the mathematical relationship between force and momentum to prove that invisible gases must be escaping despite their observational silence. Only left astronomers with the puzzle of an object that behaves like a comet while appearing completely inactive to every technique designed to detect cometary activity. The scientific community begins to grapple with Oumuamua's contradictory nature through a proliferation of theoretical models, each attempting to reconcile the object's comet-like acceleration with its asteroid-like appearance. Research groups across multiple continents develop competing hypotheses, their papers appearing in rapid succession as astronomers race to explain the first interstellar visitors' puzzling behavior. The models range from conventional extensions of known physics to exotic scenarios that push the boundaries of current understanding about small body composition and evolution. Dr. Darrell Seligman at the University of Chicago proposes that Oumuamua might consist largely of hydrogen ice, a form of frozen molecular hydrogen that could sublime invisibly while providing the thrust needed to explain the observed acceleration. Hydrogen ice forms only under the extreme cold conditions of interstellar space, where temperatures hover just a few degrees above absolute zero. Such material would remain stable during the million-year journey between stars, but begin sublimating rapidly when heated by solar radiation during passage through the inner solar system. The hydrogen hypothesis elegantly addresses several puzzles simultaneously. Molecular hydrogen gas is virtually invisible to most astronomical detection methods, lacking the strong emission lines that make water vapor and other molecules easily observable. The sublimation of hydrogen ice would produce a gentle, sustained thrust that could explain Oumuamua's acceleration without creating any detectable coma or tail. The low density of hydrogen ice might also account for the object's unusual strength-to-weight ratio, allowing it to maintain structural integrity despite rapid rotation. Computer simulations of hydrogen ice sublimation suggest that Oumuamua would need to be composed of roughly 50% hydrogen ice to generate the observed acceleration while remaining undetectable to current instruments. This composition implies formation in an extremely cold environment, perhaps in the outer regions of a planetary system where temperatures never exceeded 20 degrees Kelvin. Such conditions exist beyond the orbits of ice giant planets, in the realm of scattered disk objects and long-period comets that rarely approach their parent stars. Alternative theories focus on the possibility that Oumuamua represents a fragment of a larger body disrupted during its interstellar journey or shortly before its ejection from its parent system. Dr. Yun Zhang at the Laboratoire Lagrange in France develops models of tidal disruption events, where close encounters with massive planets or stars could fragment larger objects into elongated shards like the one observed. These fragmentation scenarios might expose fresh, volatile-rich material from the interior while creating the extreme aspect ratio observed in Oumuamua's shape. The fragmentation models suggest that freshly exposed interior material might contain volatile species different from those typically found on comet surfaces. Subsurface layers, protected from space weathering during the interstellar journey, could preserve primordial ices or organic compounds that sublime at lower temperatures than conventional cometary materials. The exposure of such materials during a recent fragmentation event might explain why Oumuamua shows evidence of outgassing despite its apparently inactive surface. Dr. Avi Loeb at Harvard University explores more speculative possibilities, suggesting that Oumuamua's acceleration might result from radiation pressure acting on an unusually lightweight or geometrically optimized structure. Solar radiation carries momentum that can influence the motion of objects with high surface area to mass ratios, similar to the way light pressure affects the motion of spacecraft equipped with solar sails. For radiation pressure to explain Oumuamua's acceleration, the object would need to be either extremely thin, perhaps a flattened sheet only meters thick, or composed of material with unusually low density. The radiation pressure hypothesis leads to exotic structural models where Oumuamua might represent a thin, sail-like object tumbling through space. Such configurations could arise naturally through tidal disruption of larger bodies, where gravitational forces stretch and flatten material into pancake-like shapes. Alternatively, the object might represent a fragment of a larger disrupted body that retained an unusual geometry optimized for interaction with electromagnetic radiation. Thermal stress models, developed by teams at the University of Maryland and elsewhere, explore whether repeated heating and cooling cycles during Oumuamua's journey might have created internal fractures that facilitate outgassing at lower temperatures than normal sublimation. The extreme temperature variations experienced during rotation from direct solar heating to shadowed regions near absolute zero could create thermal fractures that expose subsurface volatiles to space. These fractures might act as conduits for gas release while remaining too small to affect the object's overall structural integrity. The fracture models suggest that Oumuamua's elongated shape might actually enhance thermal stress effects. Since the extreme aspect ratio creates large temperature gradients between sunlit and shadowed regions, computer simulations indicate that objects with length-to-width ratios greater than 5:1 experience thermal stresses that can exceed the tensile strength of typical rocky materials, potentially creating networks of microscopic fractures that facilitate volatile release without visible outgassing. Compositional models focus on the possibility that Oumuamua contains unusual mixtures of materials not represented in our solar system's inventory of small bodies. Dr. Jennifer Bergner at the University of California, Berkeley, investigates whether irradiation of organic-rich surfaces during interstellar travel might create volatile species that sublime at temperatures lower than typical cometary ices. Cosmic ray bombardment over millions of years could gradually convert stable organic compounds into more volatile derivatives that would begin outgassing when Oumuamua first encounters significant solar heating. The irradiation model suggests that space weathering processes operating during interstellar travel might actually create rather than destroy volatile materials. Contrary to conventional expectations, high-energy cosmic ray particles could break chemical bonds in complex organic molecules, creating smaller, more volatile fragments that remain trapped within the porous surface structure until heated by solar radiation. This process might explain why Oumuamua shows no obvious signs of ice-rich composition, yet exhibits behavior consistent with volatile outgassing. Statistical analysis of Oumuamua's properties relative to known solar system objects reveals that several of its characteristics, extreme elongation, rapid rotation, anomalous acceleration, lie at the extreme ends of observed distributions. Dr. Matthew Knight at the University of Maryland argues that this clustering of unusual properties suggests either a formation mechanism fundamentally different from processes operating in our solar system, or post-formation modification during the interstellar journey that has no equivalent among gravitationally bound objects. The convergence of multiple unusual properties in a single object raises questions about whether Oumuamua represents a typical interstellar visitor or an exceptional case that happened to be the first detected. Computer simulations of interstellar object populations suggest that most such visitors should resemble conventional asteroids or comets, with only a small fraction exhibiting the extreme characteristics observed in Oumuamua. The discovery of additional interstellar objects will provide crucial tests of whether such unusual properties are common or rare among nomadic bodies traveling between stars. Only took the imagination of dozens of research teams to generate plausible explanations for Oumuamua's mysterious behavior. Only needed the application of known physics pushed to extreme limits to account for its contradictory properties. Only left the question of which theoretical model best captures the true nature of this enigmatic messenger from the depths of interstellar space. The hydrogen hypothesis crystallizes into mathematical precision through the careful theoretical work of Dr. Darrell Seligman and his colleagues, who demonstrate that molecular hydrogen ice could provide an elegant solution to Oumuamua's paradoxical behavior. Their models begin with the fundamental physics of hydrogen phase transitions, exploring how the lightest element in the universe behaves under the extreme conditions of interstellar space. At temperatures below 14 degrees Kelvin, molecular hydrogen can condense into solid form, creating a crystalline ice that remains stable for millions of years in the cold vacuum between stars. The formation of hydrogen ice requires conditions so extreme that they exist nowhere in our solar system today, but may have been common in the outer regions of planetary systems during their early formation epochs. Computer simulations suggest that Oumuamua could have accreted substantial amounts of hydrogen ice if it formed beyond the orbit of ice giant planets, in regions where stellar heating never raised temperatures above the hydrogen condensation threshold. Such locations exist in the scattered disk regions of most planetary systems, where objects orbit at hundreds of astronomical units from their parent stars. The sublimation properties of hydrogen ice under solar heating create precisely the type of invisible outgassing that could explain Oumuamua's acceleration without producing detectable atmospheric signatures. As solar radiation warms the object's surface above 14 degrees Kelvin, hydrogen ice begins converting directly from solid to gas through sublimation. The resulting molecular hydrogen gas carries no strong spectroscopic signatures in visible or infrared light, making it essentially invisible to conventional astronomical detection methods designed to identify water vapor, carbon dioxide, and other common volatile species. Dr. Jennifer Bergner at the University of California, Berkeley, extends the hydrogen ice model by investigating how cosmic ray irradiation during interstellar travel might actually create rather than destroy volatile hydrogen compounds. Her calculations suggest that high-energy galactic cosmic rays, bombarding Oumuamua's surface continuously during its million-year journey, could break down water ice and organic molecules into hydrogen-rich fragments. These radiolysis products would accumulate in the object's subsurface layers, creating a reservoir of volatile material that begins outgassing only when solar heating penetrates beneath the processed surface. The radiolysis mechanism provides a pathway for Oumuamua to acquire hydrogen-rich volatiles even if it did not originally form with significant hydrogen ice content. Laboratory experiments demonstrate that cosmic ray bombardment of ice mixtures containing water, methane, and ammonia, common constituents of outer solar system objects, produces molecular hydrogen as a primary byproduct. Over million-year timescales, this process could convert a substantial fraction of Oumuamua's original volatile inventory into hydrogen gas trapped within its porous interior structure. Temperature modeling of hydrogen sublimation from Oumuamua's surface reveals that the process would be most efficient near the object's subsolar point, where direct solar heating creates the highest surface temperatures. The extreme elongation of the object means that only a small fraction of its total surface area receives direct solar illumination at any given time, concentrating the outgassing into a narrow region that rotates around the object as it tumbles through space. This geometric effect could explain why the acceleration appears to average out over multiple rotation periods, despite the directional nature of thermal heating. The hydrogen outgassing model requires precise calibration to match both the magnitude and timing of Oumuamua's observed acceleration. Dr. Seligman's team calculates that the object would need to lose roughly 0.01% of its total mass as hydrogen gas to produce the measured non-gravitational forces. For an object with Oumuamua's estimated dimensions, this corresponds to a hydrogen ice content of approximately 50% by mass, a composition dominated by the lightest volatile material in the universe. Such extreme hydrogen enrichment challenges conventional understanding of planetesimal formation. Since hydrogen ice cannot condense in environments where heavier volatiles like water and carbon dioxide remain gaseous, the formation of hydrogen-rich objects like Oumuamua would require either unusual thermal conditions in their parent system or subsequent processing that preferentially removed heavier volatile species while preserving hydrogen. Both scenarios suggest formation mechanisms or evolutionary pathways not represented among objects in our own solar system. Observational tests of the hydrogen hypothesis focus on detecting the subtle signatures that might remain even if the hydrogen gas itself proves invisible. Radio telescopes search for the 21-centimeter emission line of neutral hydrogen atoms, though the expected signal strength lies far below current detection thresholds. Infrared observations probe for thermal anomalies that might indicate subsurface volatile loss, while UV spectroscopy searches for the faint fluorescent signatures produced when solar radiation ionizes hydrogen molecules in Oumuamua's tenuous atmosphere. The hydrogen model also makes specific predictions about the object's density and internal structure that could be tested through future observations of similar interstellar visitors. Objects composed of 50% hydrogen ice should exhibit bulk densities significantly lower than typical rocky asteroids, approaching values characteristic of the most porous cometary nuclei. The rapid sublimation of hydrogen ice should also create internal voids and structural modifications that might affect the object's rotation period or mechanical stability. Dr. Alan Jackson at Arizona State University investigates whether hydrogen ice objects could survive the typical million-year timescales of interstellar travel, given the continuous bombardment by cosmic rays and occasional heating by stellar encounters. His calculations suggest that hydrogen ice remains stable in the cold interstellar medium, with sublimation losses occurring only during rare close approaches to other stars or the final phases of entry into planetary systems. The thermal protection provided by overlying layers of space-weathered material could preserve substantial hydrogen ice reserves in the object's interior. The survival calculations reveal a delicate balance between preservation and loss of hydrogen volatiles during interstellar journeys. Objects that travel too close to other stars during their wandering risk losing their volatile inventories through thermal heating, while those that experience major collisions or fragmentation events might expose fresh hydrogen ice to space and accelerate sublimation rates. Oumuamua's current outgassing behavior might thus represent a brief phase in its evolution, triggered by its first significant heating in millions of years. Theoretical studies of hydrogen ice formation in planetary systems suggest that such objects might be relatively common products of the planet formation process, particularly in systems with massive outer planets capable of scattering small bodies to extreme distances. The efficiency of hydrogen ice accretion depends on the specific thermal history of the planetary nebula, with rapid cooling rates favoring the preservation of hydrogen volatiles in solid form. Systems that experience delayed formation of gas giant planets might produce larger populations of hydrogen-rich planetesimals. The hydrogen hypothesis transforms Oumuamua from a unique anomaly into a potential representative of a widespread class of interstellar objects, suggesting that many similar hydrogen-rich bodies drift undetected through the galaxy. Future sky surveys designed to identify interstellar visitors might need to develop new strategies for recognizing objects that outgas invisibly, relying on precise astrometric monitoring rather than traditional searches for cometary activity to identify members of this elusive population. Only took the physics of the universe's most abundant element to potentially solve Oumuamua's central mystery. Only needed hydrogen ice formation in the coldest regions of space to explain invisible outgassing from an apparently inert surface. Only left the challenge of detecting future hydrogen-rich interstellar visitors before they fade beyond the reach of current observational capabilities. 2 years after Oumuamua's discovery, the cosmos delivers a second messenger from the depths of interstellar space. On August 30, 2019, amateur astronomer Gennady Borisov, observing from his private observatory in Crimea, notices an unfamiliar, fuzzy object moving through the constellation Gemini. Unlike the stark point of light that characterized Oumuamua, this new visitor displays the unmistakable appearance of an active comet, a bright central nucleus surrounded by a glowing coma of gas and dust, with a faint tail stretching away from the direction of the sun. The object receives the designation 2IY Borisov, marking it as the second confirmed interstellar visitor to our solar system. Initial observations quickly establish its hyperbolic trajectory, confirming that this comet originates from beyond the gravitational boundaries of our sun's influence. Yet, in every other respect, 2I Borisov behaves exactly as astronomical theory predicts an interstellar comet should behave, a stark contrast to Oumuamua's puzzling characteristics that had challenged conventional understanding for the preceding 2 years. Dr. Piotr Guzik at the Jagiellonian University leads early spectroscopic observations of 2I Borisov, his team coordinating observations across multiple observatories as the comet approaches its closest passage to the Sun. Their spectra reveal the familiar signatures of water vapor, carbon monoxide, and cyanogen, the same volatile species that characterize comets throughout our solar system. The gas production rates follow predictable patterns based on solar heating, increasing steadily as the comet approaches perihelion and decreasing as it recedes into the outer solar system. The nucleus of 2I Borisov measures approximately 1 kilometer in diameter, significantly larger than Oumuamua but still modest by cometary standards. Photometric observations reveal a rotation period of roughly 7.3 hours, remarkably similar to Oumuamua's tumbling rate, though this may represent coincidence rather than any fundamental relationship between the two interstellar visitors. The comet's coma develops symmetrically around the nucleus, showing none of the directional jets or asymmetric features that might suggest unusual internal structure or composition. Detailed analysis of the comet's dust production reveals particles with properties closely resembling those found in solar system comets, particularly objects originating in the Kuiper belt and Oort cloud regions beyond Neptune's orbit. The dust grains exhibit the reddish coloration characteristic of organic-rich materials that have undergone space weathering, suggesting that 2I Borisov's surface has experienced similar processing during its interstellar journey. This compositional similarity implies that planet formation processes in 2I Borisov's parent system operated under conditions broadly similar to those that shaped our own solar system's architecture. The carbon monoxide abundance in 2I Borisov's coma provides particularly valuable information about its formation environment and thermal history. Carbon monoxide ice sublimes at temperatures around 25 degrees Kelvin, making it one of the most volatile substances commonly found in cometary nuclei. The detection of strong carbon monoxide emission suggests that 2I Borisov formed in an extremely cold environment and has never experienced significant heating since its ejection from its parent system. This pristine preservation of highly volatile materials contrasts sharply with Oumuamua's apparent lack of any detectable volatiles. Dr. Stefano Bagnulo at the Armagh Observatory leads polarimetric observations designed to probe the structure and composition of dust particles in 2I Borisov's coma. Polarization measurements reveal information about particle size distributions, porosity, and composition that cannot be obtained through conventional photometry or spectroscopy. The results suggest dust properties remarkably similar to those found in long-period comets from our own Oort cloud, implying that similar dust formation and processing mechanisms operate in planetary systems throughout the galaxy. Radio observations with the Atacama Large Millimeter Array provide unprecedented detail about the molecular composition of 2I Borisov's outgassing. The detection of hydrogen cyanide, methanol, and formaldehyde in the comet's coma reveals a complex organic chemistry similar to that observed in the most primitive comets in our solar system. These molecules serve as traces of the chemical conditions present in the outer regions of 2I Borisov's birth system, suggesting that carbon-rich chemistry develops in similar ways around different types of stars. The orbital dynamics of 2I Borisov provide clues about its ejection mechanism and subsequent interstellar journey. The comet's trajectory suggests it approached from the direction of the constellation Cassiopeia, though tracing its path backward through the galaxy proves challenging due to the gravitational influences of nearby stars encountered during its million-year journey. Statistical analysis of local stellar motions suggests several possible parent systems, though none can be identified with certainty as the comet's origin point. Comparison between 2I Borisov and Oumuamua reveals the stark differences between these two interstellar messengers. Where Oumuamua appeared inactive and asteroid-like despite its comet-like acceleration, 2I Borisov behaves exactly as theory predicts for an icy comet heated by solar radiation, where Oumuamua exhibited extreme elongation unprecedented among solar system objects. 2I Borisov displays conventional proportions similar to typical cometary nuclei, where Oumuamua showed no detectable outgassing despite clear evidence of acceleration. 2I Borisov produces easily observable gas and dust clouds that match theoretical predictions. The contrasting properties of these two interstellar visitors suggest that the population of objects traveling between stars exhibits considerable diversity, ranging from conventional comet-like bodies to exotic objects with properties not represented in our solar system's inventory. This diversity implies that planet formation and evolution processes vary significantly among different stellar systems, producing distinct populations of small bodies with characteristic compositions and physical properties. Thermal modeling of 2I Borisov's nucleus suggests an internal structure dominated by water ice mixed with rocky dust and organic compounds, a composition broadly similar to comets formed in our own solar system's outer regions. The comet's behavior during its passage through the inner solar system follows predictable patterns based on established models of cometary physics, providing confidence that fundamental physical processes operate consistently across different planetary systems. The discovery of 2I Borisov validates theoretical predictions about the population of interstellar comets, while highlighting the unusual nature of Oumuamua's properties. Most interstellar visitors should indeed behave like conventional comets when heated by solar radiation, making Oumuamua's anomalous characteristics even more puzzling in comparison. The existence of at least one normal interstellar comet suggests that Oumuamua represents either an unusual class of objects or has undergone modification processes not experienced by typical interstellar wanderers. Observational campaigns continue to monitor 2I Borisov as it recedes from the Sun, tracking changes in its activity level and coma structure as solar heating decreases. The comet remains detectable much longer than Oumuamua due to its larger size and ongoing gas production, providing extended opportunities to study an interstellar visitor in detail. These prolonged observations offer insights into how objects from other stellar systems respond to the changing thermal environment they experience during passage through our solar system. Only took 2 years for the universe to provide a second example of interstellar visitors for comparison. Only needed one conventional comet to highlight how unusual Oumuamua's properties truly were. Only left astronomers to wonder whether most interstellar objects resemble familiar comets or whether the cosmos harbors populations of exotic wanderers unlike anything in our solar system's family. The third interstellar visitor announces itself not through dramatic discovery, but through the patient process of scientific revision. On June 13, 2018, the Asteroid Terrestrial Impact Last Alert System ATLAS detects what initially appears to be an unremarkable near-Earth asteroid, catalogued as A2017U7. The object follows a seemingly ordinary orbit that brings it within Earth's vicinity, showing none of the obvious hallmarks of interstellar origin that made Oumuamua and 2I Borisov immediately recognizable as visitors from beyond our solar system's boundaries. For nearly 2 years, A2017U7 remains classified among the growing population of small asteroids that populate the inner solar system, its true nature hidden beneath the mathematical complexities of orbital mechanics. The object's trajectory appears consistent with membership in our Sun's gravitational family, albeit following an unusually elongated path that carries it from the inner asteroid belt to distances beyond Jupiter's orbit. Only through increasingly precise orbital calculations does the deeper truth gradually emerge from the accumulated observations. Dr. Robert Werrick, the same astronomer who first identified Oumuamua 3 years earlier, leads the team that recognizes A2017U7's interstellar nature. Advanced orbital integration techniques, tracking the object's motion backward through time with unprecedented precision, reveal that its trajectory becomes hyperbolic when extended into the past. The mathematics show that A2017U7 approached our solar system from interstellar space, following a path that brought it within 23 million kilometers of the Sun before beginning its outward journey toward the constellation Perseus. The object receives the new designation 3I Atla in recognition of its interstellar origin, becoming the third confirmed visitor from beyond our solar system. Yet, unlike its predecessors, 3I Atlas remained virtually undetectable during its closest approach to the Sun, passing through the inner solar system in late 2018 and early 2019 without triggering any of the automated detection systems designed to identify potentially hazardous asteroids or unusual cometary activity. Retrospective analysis of archived observations reveals why 3I Atlas evaded detection during its most observable phase. The object reached its maximum brightness while positioned in the same general direction as the Sun, making it accessible only during brief twilight observation windows when atmospheric scattering and solar glare severely compromise visibility. By the time 3I Atlas moved into darker sky regions suitable for detailed study, it had already passed perihelion and begun fading as increasing distance reduced both solar illumination and apparent size. The size of 3I Atlas proves difficult to determine precisely due to uncertainties in its reflectivity and geometric properties. Photometric observations suggest a diameter between 1 and 4 kilometers, making it potentially the largest of the 3 confirmed interstellar visitors, but also the most poorly characterized due to limited observational coverage. The object's brightness variations indicate a rotation period of approximately 5 hours faster than either Oumuamua or 2I Borisov, and approaching the theoretical limit for gravitationally bound rubble piles. Dr. Matthew Payne at the Harvard-Smithsonian Center for Astrophysics coordinates efforts to extract maximum information from the limited observations of 3I Atlas obtained before its discovery of interstellar origin. His team employs sophisticated statistical techniques to combine sparse photometric data with orbital constraints, attempting to characterize the object's physical properties despite the paucity of direct measurements. The analysis suggests surface reflectivity consistent with dark, carbon-rich materials similar to primitive asteroids found in the outer regions of our solar system. The orbital characteristics of 3I Atlas provide clues about its journey through the galaxy and possible origin system. The object approached our solar system with a velocity of approximately 12 kilometers per second, relative to the local standard of rest significantly slower than both Oumuamua and 2I Borisov. This relatively low velocity suggests either a nearby origin system or a complex gravitational history involving multiple stellar encounters that modified its interstellar trajectory over millions of years. Attempts to trace 3I Atlas backward through its galactic orbit prove challenging due to the uncertainties inherent in modeling stellar motions over million-year timescales. Computer simulations suggest several possible encounter scenarios with nearby star systems during the past 10 million years, though none can be identified definitively as the object's point of origin. The gravitational influences of passing stars, molecular clouds, and the galactic tide all contribute to orbital uncertainties that compound over the extended timescales of interstellar travel. The rapid rotation of 3I Atlas raises questions about its internal structure and mechanical properties. Objects spinning with periods shorter than 3 hours risk disruption by centrifugal forces unless they possess sufficient tensile strength to resist the outward acceleration experienced by surface materials. This constraint suggests that 3I Atlas either consists of relatively coherent rocky material or represents a rubble pile held together by cohesive forces stronger than gravitational attraction alone. Spectroscopic observations of 3I Atlas remain limited due to the object's faintness and unfavorable observing geometry during most of its detectability window. The available spectra suggest a neutral to slightly reddish color consistent with space-weathered surfaces rich in organic compounds, similar to the spectral properties observed in primitive asteroids and cometary nuclei. However, the low signal-to-noise ratio of these observations prevents detailed compositional analysis or identification of specific mineral or molecular absorption features. The lack of detectable cometary activity in 3I Atlas, despite its passage within 0.15 astronomical units of the Sun, suggests either a composition dominated by refractory materials or complete depletion of volatile species during its interstellar journey. The object shows no evidence of gas or dust production even during its closest solar approach, when surface temperatures should have exceeded 400 degrees Celsius on the sunlit hemisphere. This thermal inactivity resembles Oumuamua's behavior, though 3I Atlas exhibits no detectable non-gravitational acceleration that might indicate invisible outgassing. The discovery circumstances of 3I Atlas highlight the observational challenges inherent in identifying interstellar visitors, particularly those that approach the Sun from directions that place them in crowded stellar fields or against bright sky backgrounds. The object's extended residence in our solar system, first detected in 2018 but not recognized as interstellar until 2020, demonstrates that additional interstellar visitors may already exist in astronomical databases, awaiting the computational resources and analytical techniques needed to recognize their true nature. Statistical analysis of the 3 confirmed interstellar detections suggests that many more such objects pass through our solar system unrecognized, either because they remain below current detection thresholds or because their orbital characteristics do not immediately reveal their extrasolar origin. Improved sky survey capabilities and more sophisticated orbital analysis techniques will likely identify additional interstellar visitors in both future observations and archival data from past astronomical campaigns. The diverse properties exhibited by Oumuamua, 2I Borisov, and 3I Atlas begin to reveal the range of objects that populate interstellar space, from conventional comet-like bodies to exotic visitors with unprecedented characteristics. Each detection adds to the emerging understanding of how planetary systems throughout the galaxy produce and disperse small bodies into the cosmic medium, creating a vast population of nomadic objects that carry chemical and physical information between stellar neighborhoods. Only took 2 years of patient orbital analysis to recognize the third interstellar visitor hiding among conventional solar system objects. Only needed increasingly precise mathematical techniques to reveal 3I Atlas's extrasolar origin from seemingly ordinary observations. Only left astronomers to wonder how many other interstellar messengers remain unrecognized in the vast databases of astronomical observations. 3 points of light scattered across the observational record begin to sketch the outlines of a vast, invisible population drifting through the galaxy. Oumuamua, 2I Borisov, and 3I Atlas represent the first tentative glimpses of interstellar space's nomadic inhabitants, objects ejected from their birth systems eons ago, now wandering between stars in numbers that statistical models suggest reach into the trillions. Each detection provides a single data point in what astronomers recognize must be an enormous and diverse census of refugees from planetary formation processes throughout the Milky Way. Dr. Alan Stern at the Southwest Research Institute leads theoretical studies that attempt to extrapolate from these 3 confirmed detections to the broader population of interstellar visitors. His calculations suggest that objects the size of Oumuamua pass through our solar system at a rate of roughly 1 per year, though most remain undetected due to their small size and rapid motion. Larger objects, comparable to 2I Borisov, visit perhaps once per decade, while kilometer-sized bodies like 3I Atlas may transit our neighborhood only once per century. The detection biases inherent in current astronomical surveys heavily favor objects that either produce visible cometary activity or pass close enough to Earth to appear bright against the background sky. This observational selection effect means that the 3 confirmed interstellar visitors likely represent only the most conspicuous members of a much larger population. Inactive objects following trajectories that do not bring them close to Earth remain largely invisible to current detection capabilities, creating a hidden census of interstellar wanderers that vastly outnumbers the confirmed discoveries. Computer simulations of planetary system evolution suggest that every star produces substantial numbers of interstellar wanderers during the chaotic early phases of planet formation. Dr. Sean Raymond at the Laboratoire d'Astrophysique de Bordeaux develops models showing that gravitational scattering by massive planets routinely ejects 10 to 100 times more material than remains gravitationally bound in the final planetary system. These ejection processes operate most efficiently during the migration of gas giant planets, when orbital instabilities can scatter entire populations of planetesimals into interstellar space. The diversity observed among the 3 confirmed interstellar visitors, from Oumuamua's extreme elongation and mysterious acceleration to 2I Borisov's conventional cometary behavior to 3I Atlas's rapid rotation and apparent inactivity, suggests that the broader population encompasses objects with properties spanning the full range of possible compositions and formation histories. This variety reflects the diverse conditions present in planetary systems throughout the galaxy, where different stellar masses, metallicities, and dynamical architectures produce distinct populations of small bodies. Statistical analysis of the orbital properties of confirmed interstellar visitors reveals patterns that constrain models of their ejection mechanisms and subsequent galactic evolution. The velocities at which these objects approach our solar system, ranging from 12 to 26 kilometers per second relative to the Sun, provide information about the typical speeds imparted during planetary ejection events and modified by subsequent gravitational encounters during interstellar travel. These velocities cluster around values predicted by simulations of planet formation and galactic dynamics. The directions from which interstellar visitors approach our solar system appear randomly distributed across the sky, consistent with expectations for objects that have undergone extensive gravitational scattering during their million-year journeys through the galaxy. However, subtle statistical correlations might emerge as larger samples accumulate, potentially revealing preferred directions associated with nearby stellar nurseries or the remnants of ancient star-forming regions that produced enhanced populations of nomadic objects. Dr. Jennifer Bergner at the University of California, Berkeley, investigates whether the chemical compositions inferred for interstellar visitors provide insights into the diversity of planetary formation environments throughout the galaxy. The presence of organic-rich materials on Oumuamua and 3I Atlas, combined with the conventional volatile inventory of 2I Borisov, suggests that carbon-based chemistry develops consistently in the outer regions of planetary systems regardless of their specific stellar environment or metallicity. The survival of different material types during interstellar travel depends critically on the thermal and radiation environment encountered during million-year journeys through space. Objects that pass close to other stars during their wandering risk losing volatile inventories through thermal heating, while those that avoid stellar encounters may preserve primordial ices and organic compounds that provide direct samples of conditions in their origin systems. The chemical state of interstellar visitors thus carries information not only about their birth environments, but also about their subsequent galactic histories. Theoretical models of interstellar object populations predict that the observable sample represents only the smallest fraction of the total census, with most visitors remaining too small or distant for detection by current astronomical surveys. Objects smaller than 100 meters in diameter, which likely constitute the majority of interstellar visitors by number, produce signals too faint for detection except during the closest possible approaches to Earth. The vast majority of the interstellar population thus remains invisible, detectable only through their collective gravitational effects or occasional impacts with solar system bodies. The age distribution of interstellar objects provides another window into galactic history and stellar evolution processes. Objects ejected during the early phases of planetary system formation several billion years ago should still populate interstellar space today, having survived the gentle radiation environment and rare stellar encounters that characterize typical galactic orbits. These ancient wanderers might preserve chemical signatures of stellar nucleosynthesis and planetary formation processes that operated when the galaxy was significantly younger and more chemically primitive. Advanced statistical techniques attempt to extract population-level information from the limited sample of confirmed detections, using Bayesian analysis and machine learning approaches to infer the properties of the unobserved majority from the characteristics of detected objects. These analyses suggest that interstellar visitors exhibit a wide range of sizes, compositions, and physical properties, reflecting the diversity of planetary systems and formation processes throughout galactic history. The three-dimensional distribution of interstellar objects throughout the galaxy remains largely unconstrained by current observations, though theoretical models predict that most reside in the galactic disk where stellar densities are highest and planetary formation has been most active. The vertical distribution of these objects above and below the galactic plane provides information about the typical velocities imparted during ejection and the subsequent effects of galactic gravitational fields on their orbital evolution. Future detection prospects depend on the development of more sensitive astronomical surveys capable of identifying smaller and more distant interstellar visitors. Projects like the Large Synoptic Survey Telescope promise to increase detection rates by orders of magnitude, potentially identifying dozens of interstellar objects annually and providing the statistical samples needed to characterize population-level properties. These expanded catalogs will reveal whether the extreme characteristics of Oumuamua represent rare outliers or common features of the interstellar population. The recognition that interstellar visitors regularly traverse our solar system transforms understanding of the local cosmic environment from an isolated stellar neighborhood to an active participant in galactic exchange processes. Our solar system becomes not just a gravitationally bound collection of planets and small bodies, but also a transit corridor for materials ejected from stellar systems throughout the galaxy, creating opportunities for chemical and isotopic exchange on scales far larger than previously appreciated. Only took 3 confirmed detections to begin mapping the invisible population of objects drifting between stars. Only needed basic statistical analysis to infer the existence of trillions of nomadic bodies carrying stories from throughout the galaxy. Only left astronomers to develop the observational capabilities needed to census this vast and diverse population of interstellar wanderers. Through the gravitational architecture of the Milky Way, a vast conveyor system operates on timescales that dwarf human civilization, carrying material between stellar systems in a process of cosmic recycling that has continued for billions of years. Every star system contributes to this galactic exchange, ejecting small bodies during the chaotic phases of planetary formation and occasionally capturing visitors from other stellar neighborhoods. The 3 confirmed interstellar objects represent fleeting glimpses of this enormous migration, visible for brief moments as they pass through our local gravitational environment before continuing their journeys toward distant stars. Computer simulations of galactic dynamics reveal that the Milky Way contains approximately 10^26 interstellar objects larger than 1 meter in diameter, a number so vast that it challenges comprehension, representing more wandering bodies than there are stars in the observable universe. These objects drift through the galaxy's spiral arms and between them, following complex trajectories shaped by the gravitational influences of stars, molecular clouds, and the galaxy's overall mass distribution. Their motions create a 3-dimensional web of material exchange connecting every planetary system to its galactic neighbors across distances measured in tens of thousands of light-years. Dr. Corinne Baylor-Jones at the Max Planck Institute for Astronomy develops detailed models of how interstellar objects navigate the galaxy's gravitational landscape over million-year timescales. His calculations show that most objects follow roughly circular orbits around the galactic center, similar to the motion of stars themselves, but with additional random velocities imparted during their ejection from planetary systems. These orbital characteristics mean that interstellar visitors to our solar system arrive from all directions in space, carrying with them chemical and isotopic signatures from stellar systems distributed throughout our local galactic neighborhood. The typical interstellar object spends roughly 99% of its existence in the cold emptiness between star systems, where temperatures hover just a few degrees above absolute zero and matter densities approach those of the best laboratory vacuum. During these extended periods of cosmic isolation, the objects undergo gradual modification through exposure to galactic cosmic rays, ultraviolet radiation from distant stars, and occasional impacts from microscopic dust grains. These space weathering processes operate so slowly that their effects accumulate only over millions of years, creating the mature, processed surfaces observed on visitors like Oumuamua and Three-Eye Atlas. Encounters with other star systems provide rare but significant perturbations to the otherwise smooth galactic orbits of interstellar objects. Statistical analysis suggests that a typical wandering body passes within 1 light-year of another star roughly once every 100 million years, experiencing gravitational influences that can substantially modify both its trajectory and rotation state. These stellar encounters also provide opportunities for capture into new planetary systems, though the probability of such events remains extremely low due to the precise velocity and geometric conditions required for gravitational binding. The chemical evolution of interstellar objects during their galactic journeys creates a form of cosmic archaeology, where surface composition and internal structure preserve information about both their origin environments and subsequent processing history. Dr. Michael Mummer at NASA's Goddard Space Flight Center investigates how cosmic ray bombardment gradually alters the molecular structure of organic compounds on interstellar surfaces, breaking down complex molecules into simpler fragments while creating new chemical species not found in terrestrial environments. Laboratory experiments designed to simulate million-year exposure to the interstellar radiation environment reveal that many organic compounds undergo significant modification, with aromatic hydrocarbons gradually converting to more volatile derivatives and simple alcohols forming through radiolysis of water ice. These processes could explain why some interstellar visitors exhibit unexpected outgassing behavior when heated by solar radiation, as accumulated radiolysis products begin sublimating at temperatures lower than their parent compounds. The galactic conveyor system operates with remarkable efficiency, distributing material ejected from young stellar systems throughout the galaxy's disk and spiral arms. Computer models suggest that objects ejected from our own solar system during its early formation now populate a spherical volume roughly 1,000 light-years in radius, while our current inventory of interstellar visitors originated from a similarly large region of space. This material mixing process ensures that every planetary system contains chemical contributions from hundreds or thousands of other stellar neighborhoods. Isotopic analysis of meteorites provides indirect evidence for the ancient delivery of interstellar material to our solar system, with certain rare isotopes showing abundance patterns that differ from typical solar system values. These isotopic anomalies may represent chemical signatures of interstellar dust or larger objects that impacted planets and asteroids during the solar system's early history, when the flux of interstellar visitors was likely much higher than current rates due to the denser stellar environment of the galaxy's youth. The three-dimensional structure of the galactic conveyor reflects the Milky Way's spiral architecture, with enhanced object densities in the spiral arms where stellar formation rates are highest and planetary systems most actively eject material. Objects traveling perpendicular to the galactic disk experience different gravitational environments than those confined to the disk plane, leading to distinct population characteristics and evolutionary histories. This vertical stratification means that interstellar visitors approaching from high galactic latitudes may have originated in stellar systems with properties significantly different from our local solar neighborhood. Temporal variations in the interstellar visitor flux provide information about the galaxy's star formation history and the evolution of planetary system architectures over cosmic time. Objects ejected during the galaxy's early epochs, when stellar metallicities were lower and planetary formation processes may have operated differently, should still populate interstellar space today, though distinguishing them from more recent ejecta requires detailed compositional analysis that pushes current observational capabilities to their limits. The gravitational focusing effect of our Sun's mass creates preferential directions for interstellar object encounters, with objects approaching from certain angles experiencing enhanced gravitational deflection that increases their probability of close passage through the inner solar system. This focusing effect means that our detection statistics may not accurately represent the true directional distribution of interstellar objects in the galaxy, requiring careful modeling to extract unbiased population characteristics from observational samples. Planetary protection considerations arise from the recognition that interstellar visitors could potentially transport biological material between stellar systems. Though the extreme radiation environment and million-year timescales involved make survival of terrestrial-type life extremely unlikely. However, the possibility of exotic biochemistries adapted to interstellar conditions cannot be completely excluded, raising questions about appropriate protocols for future missions that might return samples from interstellar objects to Earth. The economic and scientific value of interstellar visitors as natural deep space probes becomes apparent when considering the technological challenges of sending human-built spacecraft to other star systems. Each interstellar object represents a free sample delivery from distant planetary systems, carrying chemical and physical information that would otherwise require interstellar missions costing trillions of dollars and taking thousands of years to complete. Future space-based observatories designed to intercept and analyze interstellar visitors could provide unprecedented insights into the diversity of planetary formation processes throughout the galaxy. Navigation charts of the galactic conveyor system will emerge as astronomical surveys identify larger samples of interstellar objects with well-determined trajectories. These charts will reveal the preferred pathways for material transport through the galaxy, identifying stellar systems that contribute disproportionately to the interstellar population and regions where gravitational focusing effects concentrate visitor fluxes. Such information could guide future searches for potentially habitable exoplanets by identifying stellar systems with particularly active histories of planetary formation and material ejection. Only took 4.5 billion years for the galactic conveyor to deliver its first confirmed messenger to human observation. Only needed 3 brief encounters to begin mapping the vast circulation system that connects every planetary system to its galactic neighborhood. Only left astronomers to appreciate the cosmic perspective in which our solar system participates in material exchange processes operating on scales that encompass the entire galaxy. The darkness between stars conceals a vast census of invisible wanderers, objects too small or distant to register in current astronomical surveys, yet numerous enough to outnumber the detected population by factors that approach infinity. For every interstellar visitor that announces itself through reflected sunlight or cometary activity, millions more pass silently through our solar system, their presence known only through statistical inference and theoretical modeling. The 3 confirmed detections represent not a complete inventory, but the first tentative samples of an ocean of nomadic bodies that flows continuously through the space around our Sun. Current detection capabilities impose severe limitations on the observable fraction of the interstellar population. Ground-based telescopes can identify objects down to roughly 50 meters in diameter during their closest approaches to Earth, while space-based observatories might detect slightly smaller targets under optimal conditions. Yet, theoretical models of planetary ejection processes suggest that objects smaller than 10 meters in diameter vastly outnumber larger bodies, creating a size distribution where the undetectable population dominates by overwhelming margins. Dr. Robert J. Dickey at the University of Hawaii leads efforts to quantify the detection biases that shape current knowledge of interstellar visitor populations. His team's calculations reveal that conventional sky surveys optimized for near-Earth asteroid detection miss approximately 99.9% of interstellar objects due to their rapid motion and unfavorable observation geometries. Objects approaching from the direction of the Sun remain undetectable until they have already passed perihelion and begun fading, while those following trajectories that do not bring them close to Earth escape detection entirely. The temporal window for detecting interstellar visitors proves frustratingly brief, with most objects remaining above detection thresholds for only a few weeks or months before fading into observational obscurity. This limited visibility means that the confirmed sample represents an extremely biased subset of the total population, favoring objects that happen to pass close to Earth during their brief transit through the inner solar system. The vast majority of interstellar visitors follow trajectories that never bring them within range of current detection capabilities. Velocity constraints further limit the observable population to objects moving within a narrow range of speeds relative to our solar system. Objects approaching at very high velocities spend too little time within detection range for identification and follow-up observations, while extremely slow visitors might be mistaken for conventional solar system objects unless their interstellar nature is revealed through careful orbital analysis. This velocity selection effect means that the detected sample may not accurately represent the true speed distribution of the interstellar population. Dr. Abraham Loeb at Harvard University investigates the possibility that some interstellar visitors might be composed of materials with such low reflectivity that they remain invisible even during close solar approaches. Dark objects with albedos similar to charcoal would appear roughly 10 times fainter than typical asteroids of the same size, pushing them below detection thresholds unless they pass exceptionally close to Earth. Such dark visitors could constitute a significant fraction of the interstellar population while remaining completely undetectable to optical surveys. The three-dimensional search volume accessible to current astronomical surveys represents only a tiny fraction of the space through which interstellar objects travel during their passage through our solar system. Most detection programs focus on regions of sky near Earth's orbital plane, where potentially hazardous asteroids are most likely to be found, but interstellar visitors approach from all directions in three-dimensional space. Objects passing above or below the ecliptic plane often escape detection due to limited survey coverage at high celestial latitudes. Statistical extrapolation from the three confirmed detections suggests that the solar system receives roughly one interstellar visitor larger than 100 meters in diameter every few months. Though the exact rate depends on uncertain assumptions about size distributions and detection probabilities, smaller objects arrive much more frequently, with meter-sized visitors potentially passing through Earth's vicinity several times per day. These estimates carry substantial uncertainties due to the limited sample size and poorly understood selection effects. The failure to detect interstellar visitors during routine meteorite impacts creates another observational challenge. Small interstellar objects that collide with Earth's atmosphere should produce distinctive meteor signatures due to their high velocities and potentially unusual compositions. Yet no meteorite has been definitively identified as having interstellar origin. This absence suggests either that interstellar impacts are extremely rare or that their signatures are too subtle to distinguish from impacts by conventional solar system debris. Advanced detection strategies under development focus on exploiting the unique properties that distinguish interstellar visitors from solar system objects. Machine learning algorithms trained to recognize hyperbolic orbits could automatically flag potential interstellar candidates from the millions of asteroid detections recorded by automated surveys. Real-time orbital determination systems might identify interstellar visitors early enough to enable detailed follow-up observations before they fade beyond detection limits. The possibility of artificial interstellar objects, technological artifacts from other civilizations, adds another layer to the detection challenge. Such objects might exhibit reflectivity properties, geometric shapes, or trajectory modifications that distinguish them from natural bodies. But identifying these signatures requires observation techniques and analysis methods not typically employed in conventional asteroid surveys. The search for extraterrestrial intelligence community has begun developing protocols for recognizing potentially artificial interstellar visitors. Gravitational microlensing effects might provide an alternative detection method for interstellar objects too small or dark for direct observation. When an interstellar visitor passes precisely between Earth and a background star, its gravitational field can briefly magnify the star's light in a characteristic pattern that reveals the presence and mass of the intervening object. However, such microlensing events are extremely rare and difficult to predict, requiring dedicated surveys monitoring millions of stars continuously. The infrared heat signatures of interstellar objects heated by solar radiation might offer another detection pathway, particularly for visitors composed of dark materials that absorb sunlight efficiently while remaining faint in reflected light. Space-based infrared telescopes could potentially identify interstellar visitors through their thermal emission even when they appear too faint for optical detection. This thermal detection strategy becomes more effective for objects that approach close to the Sun and reach elevated temperatures. Seismic monitoring networks on Earth and other planets might detect the impact signatures of small interstellar visitors that collide with solid surfaces. The high velocities characteristic of interstellar objects should produce distinctive seismic waveforms that could be distinguished from impacts by conventional meteorites or artificial objects. However, the expected impact rate is so low that decades of monitoring might be required to accumulate statistically meaningful samples. Radio observations searching for emission signatures from outgassing interstellar visitors represent another approach to detecting objects that remain invisible to optical surveys. Even minimal gas production might create detectable radio signals if sensitive enough instruments monitor appropriate frequency bands during close solar passages. The detection of radio emission would simultaneously confirm interstellar origin and provide compositional information about volatile species released during solar heating. Future space-based observatories positioned at the gravitational focus points of our solar system could achieve enhanced sensitivity for detecting distant interstellar visitors. The Sun's gravitational field acts as a natural telescope lens, focusing light from objects positioned along specific sightlines and potentially enabling detection of interstellar visitors at distances far beyond the reach of conventional telescopes. However, exploiting this gravitational lensing effect requires precise positioning of spacecraft and sophisticated image reconstruction techniques. The development of rapid response observation networks capable of coordinating multiple telescopes worldwide could maximize the scientific return from brief interstellar visitor encounters. When automated surveys identify potential interstellar candidates, these networks could immediately deploy spectroscopic, photometric, and astrometric resources to characterize the objects before they fade beyond detection limits. Such coordination requires real-time communication systems and standardized observation protocols spanning multiple institutions and countries. Only took the mathematics of detection probability to reveal how many interstellar visitors remain forever invisible to human observation. Only needed statistical analysis of 3 confirmed cases to infer the existence of vast populations traveling undetected through our cosmic neighborhood. Only left astronomers to develop new strategies for unveiling the hidden majority of objects that carry stories from distant worlds through the silent darkness of interstellar space. Each interstellar visitor carries within its physical structure a library of information written in the language of atoms and isotopes, preserving chemical signatures from planetary formation processes that occurred around distant stars billions of years ago. The rocks and ices that compose these wandering bodies condensed from the primordial disks of gas and dust that surrounded other suns during their youth, incorporating elements forged in the nuclear furnaces of previous stellar generations and distributed through space by supernova explosions and stellar winds. These ancient materials now drift between stars as cosmic messengers, bearing testimony to the diversity of planetary formation environments throughout the galaxy. The isotopic ratios preserved in interstellar objects provide the most direct evidence available about stellar nucleosynthesis processes operating in their parent systems. Different types of stars produce distinct patterns of isotopic abundances through nuclear fusion reactions that depend on stellar mass, metallicity, and evolutionary history. Dr. Catherine Altweg at the University of Bern leads theoretical studies of how these isotopic signatures should vary among objects originating from different stellar environments, creating a kind of chemical fingerprinting system that could eventually identify the parent systems of specific interstellar visitors. Oxygen isotope ratios offer particularly powerful diagnostics for tracing the stellar origins of interstellar materials. The relative abundances of oxygen, 16 oxygen-17 and oxygen-18 in planetary materials, reflect the specific mixture of elements contributed by different types of supernovae and stellar winds that enrich the molecular cloud from which their parent star formed. These isotopic signatures remain frozen into solid materials during planetary formation and should be preserved essentially unchanged during million-year journeys through interstellar space. The organic compounds detected on the surfaces of Oumuamua and other interstellar visitors carry information about the carbon chemistry that operated in their birth environments. Complex organic molecules form through a variety of processes in the outer regions of planetary systems, including gas phase reactions in protoplanetary disks, surface chemistry on dust grains, and radiation-driven synthesis in icy mantles. The specific molecular composition of these organic inventories reflects the temperature, pressure, and radiation conditions that existed during their formation epochs. Dr. Jennifer Bergner's research into cosmic ray processing of organic materials reveals how the chemical information preserved in interstellar objects undergoes gradual modification during their galactic journeys. High-energy particles continuously bombard exposed surfaces, breaking chemical bonds and creating new molecular species through radiolysis and fragmentation reactions. This space weathering process operates like a slow chemical clock, with the degree of molecular alteration providing constraints on the exposure age and radiation environment experienced during interstellar travel. Crystalline structure analysis of mineral grains in interstellar visitors could reveal information about the pressure and temperature conditions that existed during their formation in protoplanetary disks around other stars. Different mineral phases form under specific thermodynamic conditions, creating a record of the thermal history experienced by solid materials as they condensed from the gas phase and subsequently underwent processing through planetary accretion and differentiation. These mineralogical signatures should remain stable over billion-year timescales unless altered by impact metamorphism or thermal heating. The trace element compositions of interstellar rocks carry signatures of the stellar environments where their constituent materials were synthesized. Elements heavier than iron form primarily through neutron capture processes in evolved stars, with different stellar masses and metallicities producing characteristic abundance patterns. Refractory elements like platinum, iridium, and osmium should preserve these stellar nucleosynthesis signatures essentially unchanged since their incorporation into solid materials during planetary formation. Water ice preserved in the interiors of interstellar visitors represents perhaps the most direct sample available of the primordial material from which other planetary systems formed. The deuterium to hydrogen ratio in this ancient water carries information about the temperature and ionization conditions that existed in the molecular cloud from which the parent star condensed. Laboratory analysis of such samples could provide unprecedented insights into the initial conditions of star and planet formation in environments that may differ substantially from our own solar system's birth environment. Magnetic field signatures trapped in metallic grains within interstellar objects could preserve information about the magnetic environments that existed in their parent protoplanetary disks. Planetary formation occurs within magnetized disk environments where stellar and disk magnetic fields influence the dynamics of dust grain growth and planetesimal accumulation. The orientation and strength of paleomagnetic signals in interstellar visitors might reveal details about these ancient magnetic field configurations. Noble gas isotope ratios provide another powerful tool for decoding the formation histories of interstellar visitors. These chemically inert elements become trapped in crystal lattices and ice structures during planetary formation, preserving isotopic signatures that reflect both stellar nucleosynthesis and cosmic ray exposure histories. The relative abundances of neon, argon, krypton, and xenon isotopes create unique chemical fingerprints that could potentially identify families of objects originating from the same parent system. Micrometeorite analysis techniques developed for studying Antarctic ice samples could be adapted to extract and analyze microscopic particles from interstellar visitor surfaces. These particles might preserve even more pristine chemical signatures than bulk material, since their small size protects them from thermal metamorphism and impact processing. Individual dust grains could carry isotopic anomalies that provide direct samples of stellar nucleosynthesis products from specific types of stars. The amino acid and other biochemical precursor inventories of interstellar visitors offer insights into the potential for prebiotic chemistry in other planetary systems. Laboratory experiments demonstrate that complex organic molecules form readily in interstellar ice analogues when subjected to radiation processing, creating inventories of compounds relevant to the origin of life. The specific molecular compositions found in interstellar visitors could reveal whether similar prebiotic chemistry operates universally or varies significantly among different stellar environments. Comparative analysis of multiple interstellar visitors will eventually enable astronomers to identify chemical trends that reflect the diversity of planetary formation processes throughout the galaxy. Objects originating from metal-rich versus metal-poor stellar environments should exhibit systematic differences in their trace element, abundances, and isotopic compositions. High-mass versus low-mass parent stars should produce distinct nucleosynthesis signatures preserved in the materials they incorporate during planetary formation. Future sample return missions to interstellar visitors could revolutionize understanding of planetary formation processes by providing laboratory-quality chemical analysis of materials that formed around other stars. Such missions would require rapid response capabilities to intercept these fast-moving targets during their brief passage through the inner solar system. The scientific return from analyzing pristine samples of interstellar materials would be comparable to the Apollo lunar samples in terms of advancing fundamental understanding of solar system formation and evolution. The database of chemical signatures from interstellar visitors will eventually enable astronomers to construct a galactic map of stellar nucleosynthesis and planetary formation processes, revealing how these fundamental astrophysical processes vary throughout different regions of the Milky Way. This chemical cartography of the galaxy would provide insights into cosmic evolution processes operating on scales far larger than individual stellar systems, connecting planetary science to galactic astronomy through the medium of wandering interstellar objects. The preservation of volatile species in interstellar visitors offers unique opportunities to study the primordial ices from which comets and outer planets formed in other stellar systems. These materials condensed directly from the gas phase in cold, protoplanetary disk environments, trapping chemical signatures of the molecular cloud material from which their parent stars formed. Laboratory analysis of such pristine volatiles could reveal whether the water, carbon dioxide, and organic molecules that enabled life on Earth represent universal products of planetary formation or unique characteristics of our particular stellar neighborhood. Only took the physics of atomic nuclei to encode chemical information about distant stellar systems into the materials that compose interstellar visitors. Only needed the preservation properties of crystalline solids and frozen ices to maintain these signatures across million-year journeys through interstellar space. Only left human ingenuity to develop the analytical techniques required to decode these messages from other worlds and read the stories written in the language of isotopes and molecules. The astronomical community prepares for an era of enhanced interstellar visitor detection through the deployment of next-generation sky surveys and advanced observation technologies. The Large Synoptic Survey Telescope, soon to begin operations in Chile, will photograph the entire visible sky every few nights with unprecedented sensitivity, potentially increasing interstellar object detection rates by orders of magnitude